Hey Matteo, how you doing? Nice to see you. Dotted around at ADC are all these kind of little sort of sub-booths where there's all sorts of really interesting things going on. And this, rendering audio in virtual enclosed spaces from the University of Surrey, caught my eye because it's like you were explaining before we came on camera. It's like convolution, but it's not. It's real time, so it's therefore tweakable in real time. So explain a little bit about this.
So the main objective of this is aimed for the most part at video games, virtual reality applications, where you have an environment, you know all of the geometry of the environment, so you have a full description including materials of the different surfaces, you know where there's carpet or wood or glass or what have you. And in most cases, if you wanted real time or in any case, if you wanted a reverberation in this application, then you would need to fine-tune yourself. Okay, so I know that this room, I want this to sound this particular way, and fine-tune that. So you need to already have an idea of how it's going to sound, and then you need to do a lot of work to make it sound that way.
So would you generally use algorithmic reverb in that situation, or convolution? What would be the, in traditional methods?
Either. If you look at something like Rooms and Portals by TWIs, that's a fairly common one, that also using reverberators like we do, not convolution. In other case, you would use convolution, but before any of that, you need to set it up manually and know what you're doing. One of the draws of our methods is that you, starting from this description of the environment with the materials, then the computer does all of that work. It figures out where the reverberation is, which parts of the space are more or less reverberant, how much, and where that is. And all of that is pre-computation. Then when you're at runtime, so you're actually running the video game, you know you have several sound sources here and then the listener, and they move around, then you have a lot less computation to do.
Because it knows that wall is made of glass and that wall is made of carpet. Right, okay.
Not only that, but also it's already figured out all of the connections in the space. Because if you just knew what materials are where, well, that still doesn't give you the full reverberation. If you have a very reverberant environment, a cathedral or something, then even if you know all of the geometry and materials, but at real time, you need to figure out, okay, how long is the reverberation?
How far
if you
away
haven't done anything beforehand, you need to do ray tracing or some other geometrical acoustics, some computational acoustics to prepare an impulse response at runtime and then convolve that.
Which that would introduce delay, so it wouldn't be right.
It would introduce latency. It's expensive. And if you have several sound sources, several listeners, then you need to prepare an impulse response and then convolve it for each pair of source and listener.
Right.
So the number of convolutions you need to apply is number of sources times number of listeners.
Yeah, which slows things down enormously, right?
Yeah, not to mention, if it's a very reverberant environment, then you have a long impulse response. Convolution with a long impulse response, even more complex.
So how are you solving this problem?
We're solving in several ways. First, as I said, we analyze the environment and not only looking at the materials, but we figure out essentially the entire reverberation, the entire length of the reverberation, however long that might be, in pre-processing.
Right.
So without knowing where the sources and listeners are, even. And then once we do know the sources and listeners, we figure out, okay, given we have this reverberation time, if a source is here, what's the level going to be? How much energy is that source going to contribute to
it's a math calculation.
Yes.
Right.
And then instead of preparing an impulse response and convolving with it, we have a system with several reverberators in parallel, several FTNs. We have already tuned the decay rates of the FTNs such that their reverberation times match whatever reverberation time we want in the environment. What we do at runtime is we change the input and output gains of those reverberators based on where the sources are, where the listeners are.
Right.
So all of these reverberators, they really model the environment itself. They're shared by all of the sources and multiple listeners. If you have several sound sources in different positions, they're all going to feed their sound signals into the same set of reverberators for the environment at different levels depending on their positions. If you have several listeners or a single listener, but you want directional late reverberation, so essentially those are different listeners because there are different sound channels you want, then still you are going to read from the same set of reverberators and scale each channel differently depending on the positions and orientations you want for the listeners.
Right, so that result, I notice you've got like a rather smashing looking three-dimensional render here. So if I turn this up, what are we listening to here?
So what we're listening to here is an environment made of several rooms. We have two which are very reverberant to either side here. Let me show. We have a room which is plaster and cement, all flat, very reverberant. On this other side, we have a room which marble on the floor and acoustic plaster on the walls, so this is also very reverberant. But then we have an outdoor space, which is quiet, and we have a few other rooms in the back, which I'll show you. But what we have on top of all of these rooms is several sound sources. Here I'm showing bells, bass, drums, guitar. All of these are tracks on the same music. And what I can do is move the sources around to different rooms. Let's get some more in the reverberant environments. And then as I move around, myself the listener, I'm going to hear the reverberation of different sources based on where they are and where I am. If I go outside, I'm still going to hear the late reverberation because these sources are reverberating there and I am hearing it through the doorway, but quiet for the most part. I'm hearing
so
the
that, I mean, and that's multiple sources and multiple reverberators
yes.
with different spaces, and then some of them are passing through multiple spaces as well. So.
Yes, but in our case, in this setup, all of the reverberators are in parallel.
Right.
They're not in series. Whereas if you look at something like rooms and portals from WISE, those are actually reverberators feeding into each other. Now, if I go into this very quiet room, all of the sources die out.
Oh, it sounds like we're in here, apart from these kitchen porter.
Yeah. But if I turn on this plot here, we're looking at the energy decay. You can see here the base, the green one. We have this sharp decay, but then it rolls off. That's because right now with this base, we're in this reverberant environment. Yes, it's a room, but it's definitely less reverberant than the environment next door.
Yeah.
So when we're in the same space, we have that relatively short reverberation time, but even when we're there, that reverberation from the base is going into the reverberant room and then coming back. And that's why we have these longer reverberation here.
So this is presumably, I mean, in terms of a product, this is going to end up in, I'm trying to remember what the name of the game, the Unreal Engine and that's, is that where the final destination for this sort of stuff is?
That's the objective. And we also have some VR demos. I don't have it with me today, but we have set up our plugin also for using virtual reality with a headset.
Right.
Now, what I showed you, this demo, this is built in Unity, which is a game engine, but the plugin we implemented, it's just a plugin in C++. So we just built this Unity demo to showcase our plugin. You could do the same in Unreal Engine, still with our plugin. That's something we want to do in the future.
Interesting.
And
so
we're going to make these open source.
University of Surrey. So is this a commercial project or a research project?
No, it's a research project. So I developed this late reverberation technology over the course of my PhD. My colleague Josh Manal developed this plugin, which we put it into. Just recently, we merged the two things together, putting my work in the theory into his work in the plugin. And what we're doing now is simply trying to raise awareness of what we've done, of what these can achieve, both in the industry, in academia, letting more people know about this because we really think this is innovative.
So where can people kind of keep up to date with the latest papers and academic output from this project?
So for sure, if you look at our names, we have some references of our latest papers there. And I know a couple of these are behind the paywall, but if you send me or any of my colleagues an email, we'll definitely hook you up. As for the code itself, we're going to make this plugin open source pretty soon. We think in December, January, that's going to be on GitHub on our accounts. We're definitely going to publicize it on the LinkedIn and YouTube pages of our Institute of Sound Recording, so you can look there as well.
Brilliant. Thank you very much.
No worries.